All right, thanks everyone. So, let's get the conversation started. And a lot of people are curious about what is quantum. What is the definition of quantum, right? So maybe we could start off with that and give people some level of context as to what the heck is quantum. So maybe we could start off with anyone in the panelists.
Let me start off with a fairly clear definition. You might argue with it, but I say that quantum technology is really derived from physics principles that were really discovered in the 1920s. And specifically, there are two key principles. One is called superposition, where you can have basically sort of be in two states at once. And the other is entanglement, which you have two qubits linked. Einstein called it spooky action at a distance. And the interesting thing is, even though those were discovered in the 1920s, the classical computers today, even today, do not use those two physics principles. And what people have been doing over the past couple of decades is they've been figuring out ways to leverage those principles of physics to come up with new types of computers or new types of communication. So if it doesn't use those physics principles, then I would say it's classical.
So I think I would add a bit of nuance to what Doug was saying. So if we think about technology, there are plenty of technologies that we use every day that would not be possible without these quantum principles. So including things like transistors, which of course are part of all modern electronics, lasers, machines that are like very very impactful, like MRI machines, for instance. Operate based on quantum principles. So, I mean, in some ways, there is a current generation of things that you might call quantum technologies. This is not what people mean when they say quantum technologies these days. What people mean these days is sort of a more advanced generation of technologies. And, the kinds of technologies that we'll see coming out of this new generation of quantum in the next, year, 2 years, 3 years, will be certainly improvements over things that exist today, or else we would not be talking about them. But the trend in modern quantum technologies over, say, the next 5, 10, 15, et cetera, years is going to be, or is sort of about harnessing more completely and exerting more control over these principles that Doug mentioned, things like entanglement, leveraging large-scale entanglement to do interesting things. That's what makes a quantum computer work, for instance. Whereas these more simpler, earlier generation of devices operate because of quantum principles, but humans, until sort of relatively recent times, have not been able to exert as much control over and manipulate these sort of quantum properties of matter to the extent that we're now able to and will be able to in the near future.
Yeah, I think I agree with that, and maybe I'd like to kind of give a little bit more context. I think people refer to sort of these older generation of quantum technologies as the first revolution, and now we're in like quantum 2.0, where we're using these weirder quantum mechanical properties. So things like magnetism and tunneling, which are also quantum properties, gave us, what the computer, the laptop that I'm using right now. And those were certainly advances that happened over decades and are very at the heart of it is quantum mechanics. I think maybe I'd like to expand the definition a little bit to talk to include sort of properties that show up at small length scales. So this idea that we're harnessing properties that we don't see at larger length scales. So atoms as waves, we're using atom interferometers to give us quantum technologies as accelerometers and measuring time and gravity, etc. So those I would also include in our new generation of quantum technologies. So it's not a little bit beyond superposition and entanglement. I'd like to broaden it a little bit.
Okay, great. Thanks. And there's a lot of people that basically conflates, well, they're trying to figure out, what is the definition of quantum computer, right? So the world that we know right now is all about classical computing, and then quantum computing is here. A lot of people all tend to ask me, what is the difference between the two, right? As an additional context, um, uh, a lot of the people here may be more from a classical world. So can you guys give some insights as to the similarities or differences between both compute paradigms?
Yeah, so I'll give it a shot. So what I like to emphasize when it comes to something like quantum computing, as opposed to classical computing, is that quantum computing allows you to expand the list of things that you're allowed to do fundamentally, like your list of fundamental operations on, say, data. So for example, if you take like a basic calculator, you can add, subtract, multiply, divide, that kind of thing. You expand to a scientific calculator, you get new buttons like square root and exponent and things. If you have a graphing calculator, it has other stuff, like sines and cosines with buttons. All of those things are, they seem like new operations, but they are in fact all built on the same basic, add, subtract, multiply, divide underneath. What a quantum computer does is it has additional things you can do using these properties of entanglement and superposition and other stuff that you cannot easily build out of adding, subtracting, multiplying, and dividing, and those basic operations. It gives you a new set of things that you're allowed to do. And having access to that new set of things you're allowed to do as fundamental operations, explaining what those new things are takes a little bit of effort, but there is a new set of things, and that allows you to, throwing those ingredients into your algorithms allows you to take shortcuts that you would not have otherwise been able to do. The list of applications we have that take advantage of those new ingredients is not terribly long, but there are a few that are very impactful. A few algorithms we can now instantiate using those new ingredients, or we'll be able to when we have a sort of large quantum computer. That it allows us to do some very amazing things that we would not otherwise be able to do. What quantum computing is not, it's not computing that, it's not doing everything faster. It's not calculating a bunch of stuff all at the same time. It's that these kinds of things that people often say. That's not what it is. It's a few special operations which allow you to take algorithmic shortcuts. And when you can take advantage of those shortcuts, you should. But if you're not taking advantage of those special things a quantum computer can do, please don't try to use the quantum computer. Because if you're just using it to add, subtract, multiply, and divide that you could do with your other computer, you'll find it's extremely inefficient, very slow, not worth doing. It's a special like hardware accelerator device for these particular kinds of operations. That's one way that's I think the most productive way to think about it.
Okay.
Yeah, one thing I would add, there is another misconception that people believe that over the long term, quantum computers will completely replace classical computers, and that won't happen. You'll always be using those. You'll be using those together, but for things like looking at your email or browsing your website or balancing your bank book, you will always use a classical computer. As the quantum computers get more and more powerful, what you'll see, and the big trend right now in the industry, is to put together what are called hybrid systems, where you have classical computers working together with a quantum computer to solve a problem. And actually, you may have part of the algorithm run on the classical computer and another part of the quantum computer, another part of the algorithm working on the quantum computer, and each machine does what it does best.
Anything to add, Preeti?
I agree with everything that was said. I think the way I think about it is quantum computers they just do a new kind of math, and you use that new kind of math for very specific problems that it does really well, and you will continue to do the old kind of math. It's not going to go away.
Okay, great. So we have this TCA is a big angels network. So we probably have quite a bit of people here that are investors, right? And this is probably going to get shared to a lot of investors. So maybe we could talk about the trends that you guys see in the quantum technology space. So I'd like to kind of hear what you see as the trends, what you consider as low-hanging fruit versus long-term areas of quantum technologies, and I'd like to see your point of view on that.
I can get started this time. So I think from where I sit, quantum computing is many things. And one of the most exciting things about quantum computing is, how many different varieties of quantum computers we're working on. You have quantum computers kind of like the kind that Google's working on based on superconducting qubits. There's others working on trapped ion and cold atom and what have you, even electrons on helium. I think it's a very exciting time. There's, every day I'm hearing about new ones. What is really exciting to me about this industry is also all the supporting systems. So quantum computing has given rise to all these like enabling technologies, and there is just so much activity, so many amazing advances that are being made in electronics or cryostats or microwave electronics. I think regardless of when we get a fully fault-tolerant quantum computer or not, all of these other advances that are being made in enabling technologies are going to put us, have already created this entire other industry, training some very smart people on very smart problems that will, bear fruit in generations to come. To me, that's the most exciting thing about this industry.
Yeah, one thing I would add, by the way, is that although the focus has been on quantum computing, that's what people talk about the most, there are actually other branches. There's quantum communications and quantum sensing.
Yeah.
And both of those could have some very significant things on society. Quantum sensing, for example, just to give you an example, think of a GPS system that doesn't use satellites. By using quantum technology, you can come up with very good sensors that allow you to navigate. And that's an area, by the way, that the US military is very, very interested in what they call GPS-denied environments. But there's a lot of areas where you could use quantum sensing where it can do things that classical sensors can't. And then quantum communications is a way of, instead of sending bits over a fiber optic cable, you send entangled qubits over a fiber optic cable. And that allows you to do a whole bunch of things, including that's one way of not getting hacked by a quantum computer that can break the RSA encryption. But you can do other things like a blind quantum computation, where you can submit a job over the cloud and no one knows exactly what you're doing. You can also network sensors, which, a network of sensors could even be more sensitive. So there's a lot to it. It's not just computing, but communications and sensing are also going to be very interesting over the next few years.
Yeah, I'll agree. I agree completely with Doug that, if we're talking about trends, I think a trend of, obviously quantum computing will continue, but the people will start to realize that there is more to quantum technologies besides quantum sensing. More people will wake up to that and recognize that. I mean, there are already, several who are, but people will talk about it more. Whereas quantum computing likes to get the attention. I think, so definitely that. Another aspect, I think, of quantum computing, going back to the computing side that I think hasn't been mentioned so far, is the sort of trend of accessing quantum computers through the cloud. So I think this is a thing. So if you look at, say, like Amazon or Microsoft, they are standing up quantum computing like services where it may not be their quantum computer. It may be a quantum computer belonging to IonQ or something, but you would access it through, say, the Amazon service. And that's, quantum computing is likely, I think, to end up being a cloud native kind of service into the near and probably also near future and probably also the more distant future, where companies will not likely own their own quantum computers. They'll, there's a general trend in computing moving toward the cloud anyway. And for quantum computing, I think it'll just probably just start there and be that way from the beginning.
Okay, thanks. So let's move in towards more of the industry aspect of this, right? So, I've spoken to so many different folks in the finance industry, pharma, healthcare, and so on and so forth, right? And some of the confusion in this space is in the area of the use cases, right? So maybe you guys can give me a view as to what what industries would be closer to adopting this technology, right? So that's one. And then the second question is, have we really imagined the use cases quantum applies to, right? So, because our current thinking is all about classical computing and what we know about classical computing, but what about quantum? Is it the typical use cases that we see, or is there more to it that we haven't really imagined?
Well, one thing I would point out is that, in the late 1940s, when John von Neumann came up with the von Neumann architecture for computers, is what we still use today, I don't think he imagined we'd be having things like Facebook or Zoom meetings with his device. So there are going to be applications in quantum that we can't even conceive of. Again, 20, possibly maybe 30 years from now. The ones that people are working on intensively right now, though, are anything doing with computational chemistry for things like drug design or new materials discovery. We've all seen with the COVID how quickly the vaccines were done. Now, those were done, the mRNA vaccine was simulated on a classical computer, but the belief is that quantum computers in the future will allow people to develop new drugs and really reduce the cost and time it takes to develop a new drug. Finance is very interested. Both companies like JP Morgan and Goldman Sachs have quantum teams. And the reason is the payoff could be quite large. If you can get another 100 basis points of interest out of $1 billion portfolio, you're making a lot of money. And then the third area that is quite often mentioned is optimization. Almost every business, every organization has some type of optimization problem. And there's lots of work being done to figure out ways of optimizing on both gate-based quantum computers and quantum annealers. But the challenge that they have in optimization, as well as these other areas, is the classical computing people are not resting on their laurels. They are continuing to improve the classical computing too. So, the bar gets raised higher and higher, but eventually people believe that quantum will win out.
So I think so coming back for a second to sensing, Doug mentioned one industry, I think it's a good one, of like GPS denied navigation, for example. There's another industry that could have impact is, I alluded to before to things like the MRI, which are quantum devices that are really big and expensive, but with new modern quantum technology, quantum sensing technology, you could imagine something analogous to the MRI that you could use for medical diagnostics or medical imaging that would be much smaller and more portable and cheaper and easier to deploy. Things like that. People are working on things like that. In the computing space, I think, we can try to think about what might happen in the near future versus what might happen long term. I would say, when is sort of a difficult question, but I tend to believe that the areas which will be first to benefit from quantum computing, and first still might be a little ways away, but the first areas are likely those areas which have some inherently quantum aspect to them already, like computational quantum chemistry that Doug already mentioned. And I would expect that the other areas that people are working on, things like optimization, for example, which are not inherently quantum, have no, the problem itself has no quantum angle to it would probably require a more sophisticated quantum device before you would see like the real impact. So maybe some larger, more fault tolerant machine might be necessary and take longer to develop. So the first industries that I would expect to be impacted are those more inherently quantum industries, like the ones that involve atomic scale things already, like chemistry.
Yeah, I think I'd add to the, using quantum sensors, atomic clocks, things like that. Those are already applications, already commercial products in some ways. And I think talking about quantum sensing for biology, that's kind of one of these sleeper applications, but I think there's a lot of promise there. And a lot of people think that this will be an area which, kind of like single photon spectroscopy, it took a while, but now it's a very commonplace thing. So looking at this, like a decade from now, we'll be using quantum sensors for looking at, cellular environments within your body, and that will happen. It's just a matter of time.
Okay. Yeah, I just want to mention also for the folks in the audience, if you have any questions, we will take your questions a little later, but it'll be good for you to start putting something in the chat if you're interested in asking the question. And then, so a lot of people are always interested in, having a business production ready quantum system. I get this question a lot, right? So when is this business production ready quantum computer going to be around so we could make use of it? So in your own perspectives, when do you think a business production ready quantum computer could be used from, not just for training purposes, not just for development purposes, but something that has enterprise value?
I'll start. So I think, it's always very hard to put a date on a question like this. You could think about, as sort of a middle step, you could try to think about how advanced the technology might be before you really see like a business enterprise, ready use case for quantum computing, and not, differentiated from like sensing or communication or those, but for quantum computing itself. I tend to, I tend to think that it may be unlikely that we see a like business ready, a business ready use case or a use case for that is relevant to, real enterprise on quantum computing until quantum computers are advanced enough probably to do, reasonably large like fault tolerant computations. I'm not super optimistic about the near term, but I could be wrong. But even in that case, I would say the near term prospects are not the very near term. It'll be like the late near term, maybe just before we get fault tolerance. And so I'm going to reinterpret the question as when might we expect, excuse me, to see fault tolerant quantum computers. Pardon me. And it could be 5 years from now. It's probably more like 10 years from now, and perhaps longer. It's really a few engineering milestones away that there are fundamental engineering problems that we don't really yet know how to solve. It's hard to put a timeline on those, but it's probably on the order of 10 years.
Yeah, let me perhaps just talk about how I foresee the machines developing. And I'll start with a buzzword, and the buzzword is NISQ, N-I-S-Q, which stands for Noisy Intermediate Scale Quantum. The problem we have today is that, number one, the quantum computers aren't very large. The largest one is like 127 qubits, but those qubits are really bad. They fail like 1% of the time. So it's very, very difficult for anyone to put together a program when you have such an unreliable computer. And in fact, most software people who actually are actively working in the industry today will say that if they are developing an algorithm, they're probably better off using a quantum simulator which on a classical computer to fine tune their algorithm and figure out how it works. But over the next 5 years, maybe 10 years, the industry will be working in 3 different directions, 3 dimensions for improvements. The first is to increase the number of qubits scale, and the target really by, let's say, 2030 is a million what are called physical qubits. The second is to increase the quality of those qubits. So rather than failing 1% of the time, they may fail like 0.1% or 0.011% of the time. And that gets more reliable. And then on top of that, they will add error correction algorithms. So if you take a bunch of qubits that fail, let's say 0.1% of the time, and you gang them together to create what's called a logical qubit, then the failure rate could be much, much lower, like 0.001% of the time, or something even better than that. And then the third is just to increase the speed, the raw speed of the qubits. If you look at gate delays, which I do since I'm a former computer designer, quantum gates are very, very slow in comparison with classical computing gates. And that's actually one of the reasons why quantum won't replace it. But people are working to try to improve that all over. But over the next 5 years, you're going to have these non-error corrected machines called NISQ, and people are trying to come up with algorithms that can run on that. And I think a handful of people might, but probably the bulk of quantum algorithms won't find those powerful enough to beat out a classical machine. But towards the end of this decade, and I know that's what the goal is for Google and IBM and several of the others, you will start seeing these error-corrected machines, maybe 1 million physical qubits, 1,000 logical qubits. And when that happens, I think that would be sufficient to do a business-ready type of application. And of course, the question is it 5 years from now? Is it 10 years from now? And no one really knows, but we know it's not next year.
Do you have an angle on that, Pretty? I think you're muted. Okay, so we can move on. So it sounds like we have enterprises have quite a bit of time. Are you back?
Yeah, sorry that I was not able to unmute myself. I think I agree with the assessments from before. Like in 5 to 10, it's more likely 10 years from now that we'll see really what we're thinking of as quantum computers. But I do think in the meanwhile, in industries like finance, for example, where they're really searching for like the smallest advantage we can get, we will see people using current NISQ computers or existing state-of-the-art computers being used for certain applications. And I think we'll see more and more of these in the next few years. And then going back to thinking about industries like finance, I think it's not just quantum computing. One of the things that they're interested in is quantum communication and applications of that. Like we'll see a lot more of that in conjunction with quantum computing.
Okay, thanks, Pretty. So it sounds like enterprises have a bit of time, right? But this technology sometimes the pace of how technology innovation happens, it's quite different nowadays. The acceleration that's going on there is also quite exciting, right? So my question to you is, what should the enterprises be doing to get them ready for this wave of next generation computing? What should they do?
Educate themselves, be aware of what might change or what how they might need to change their business and to keep up with this change in technology. And I think, I don't know that every business needs to start hiring a team of quantum computing specialists like JP Morgan and Goldman Sachs do, but I think everyone kind of needs to know needs to know enough to think about where this might affect their business or where they might take advantage of this in their business.
Yeah, let me mention one thing about cybersecurity. There is a risk right now that enterprises face, and that is the fact that this quantum computer that we've been talking about 10 years from now may not be powerful enough to break the encryption technology that's used in the internet today, the RSA encryption. There's an algorithm called Shor's algorithm that would allow you to factor a large prime number. And even though those computers aren't available 10 years from now, there is a possibility of a adversary using what's called a harvest now, decrypt later type of approach, where they suck up all your data, all your RSA encrypted data, and they store it on a hard drive for 10 years. And then when they get that quantum computer, they would be able to break it. Now, for many types of data, that's not all that critical because not too many pieces of data actually have a shelf life of 10 years. But let's say you're transmitting the design plans of an F-35 fighter jet or someone's health records, that could be an issue. So the one thing that the government is very concerned about is there needs to be a migration to convert the encryption that's used, what's called the key exchange, to quantum resistant versions. And President Biden just, I think, signed an executive order or something telling the government agencies to get started on that. And it's a very complex process because there's going to be billions of devices that are going to have to be upgraded to use these new quantum resistant type of technologies. So the first thing I would recommend to an enterprise is they actually should look at that first, because they could face an enormous risk if their data gets exposed, even 10 years from now, and try to figure out how to plan for that.
Yeah, I'll just agree with what the other panelists have already said. Absolutely, the cyber threat is a real threat today for the reasons Doug mentioned, and so there are certain steps that one has to take. And then, yeah, in terms of investigating uses for like new products or things like that actually use a quantum computer, yeah, the best thing to do now in most cases would be to educate oneself. There's an awful lot of hype and misinformation out there regarding quantum, what it can do and what it can't do. And so basically cutting through that and getting the real story, which is, involves a certain amount of technical understanding. So there should be somebody in the organization who has they don't have to know how to build a quantum computer themselves, but should have a reasonably technical understanding of what the realistic possibilities are, so that it can be worked into a longer term roadmap.
Okay, great. Yeah, let me follow on. We have some audience questions that are connected to this current conversation right now. So one question is, would you consider quantum random number generation to be NISQ?
Yeah, that's an interesting question. So quantum random number generation, it depends on, I mean, I guess it depends on how you're generating your numbers. So most quantum random number generation, you might not even classify as like computing. NISQ usually refers to computing, like computing without error correction. So, you could have a quantum device that consists of like a single qubit that you just prepare and then measure, and it gives you a random outcome, something like that. And that's a way to get quantum random number generation. It's NISQ in the sense that it's not error corrected, but it's not really doing computation. There's another, some of you may remember reading about the possibility of doing more sophisticated kinds of random number generation that Google talked about a while back, around the time where it was doing its, beyond the first time it went beyond classical computation using a NISQ device, which I think was in 2018 or 2019. And this was basically that kind of thing would have used a quantum computer, a NISQ quantum computer, or that kind of random number generation could use a NISQ quantum computer executing a random program, a classically random program, with some, large, dozens or maybe tens or hundreds of qubits eventually to get a, well, I guess in this case, you wouldn't want hundreds of qubits, but dozens of qubits to get a sort of random string of numbers. And then, there are certain cases where that might be more interesting than just one random number at a time. And that would use a NISQ device, but generally I would say no.
Okay, thanks. Okay, and then another question we have is coming from Shaina. How do you estimate the market size for quantum computing applications? That sounds like a hard question.
I think, well, so I'll give you my take. I think it's very hard to estimate the market size for applications that don't exist. Like, I think you have to take whatever number anyone gives you with a grain of salt. Like, it doesn't mean you don't invest in these technologies. There is no question about the promise of this. But if someone tells you it's 2 billion or 200 billion or 3 trillion, it's like, how do we know? We don't know the applications that exist.
Yeah, I would agree with Preeti. It is very, very difficult to do that, but people try. And, one thing that they try to do is they look at the classical computing counterparts. For example, we do know reasonably how much people are spending on using classical computers to do computational chemistry. And that might give you a little bit of a baseline in terms of how much they might ultimately spend on quantum computing. And you might be able to forecast, if they spend so much right now in computational chemistry, how's that going to increase year over year? And perhaps what percentage of that market might be taken by quantum computing over the next 10 years. So, people do that. You can go to the consultants, BCG and McKinsey. They have some reasonable white papers out there where they try to do that. And that's probably the best we can do at this time.
Okay. In terms of the, how would you evaluate the urgency of the quantum workforce training, either for hardware technology or for application development?
I think if I'll take that question on just based on where I am sitting in the middle of educational and research institutions, and I talk to a lot of industry. I'd say that is the number one concern for in industry. It's just, how are we going to handle all of the requirements of building this industry? And that's something that educational institutions are thinking about very deeply. And I think we're going to have to be very creative, and also think about education from, not everyone needs to have a master's or a PhD in quantum technologies, but everyone needs to be exposed to it from whatever perspective makes sense. And over time, we'll build up this workforce that will be ready to grow this industry. But this is a huge problem right now.
Yeah, maybe Stefan, if you can weigh in on this one, right? So you work for a quantum technology startup. I would consider it a startup, but with a lot of stuff done there. So as from a startup point of view, how did you guys get ready?
Yeah, no, I mean, so I completely agree with what Preeti was saying. The workforce situation is workforce education is and training is a major issue. I would expand that as well. I think it's maybe a bigger issue even than just workforce training. Also, coming back to what we were saying before, sort of quantum customer training also needs the situation is kind of analogous to machine learning, I think. Everybody needs to know machine learning. Not everybody needs to be an AI research scientist, but everybody needs to understand how the basics of what machine learning means and how it could apply to their situation. And anyone who is in a technical role needs to have a deeper understanding, etc. So I think you could draw very, very close parallels between AI or ML and quantum in this case. But indeed, there is a shortage of quantum workforce, and a lot of the shortage is not. I mean, more physicists is great. I love physicists. I'm a physicist, but we also need software engineers people who are first and foremost a software engineer, but then also know enough quantum in order to be able to contribute. So they don't need a PhD or a master's in physics, but there needs to be some component of that education, and it's hard to find those kinds of people. So like we, for example, and we're not the only ones, but like in this sort of modern world of remote work, we look globally at the global workforce for things like recruiting, and it's still hard to find people who have the right kinds of skills. I can't imagine what it would be like if we had to restrict to like one geographic area.
Okay.
And I can tell you that sitting where I do, where I'm trying to connect academia and industry, I will say that the number one reason industry likes to come to academia to work with us is for the talent. It's not even the research that's happening. It's really just the talent that's being produced.
So the other question is related to more about quantum systems, right? So the question is really about building blocks. Which fields may be strongly correlated to quantum computing that will enable quantum applications, such as quantum sensing and communication?
Well, there's, a number of areas. Interesting thing about quantum is it requires a lot of different areas of expertise. Everyone understands that physics is quite critical, but also mathematics, particularly linear algebra, is very critical for quantum. But as Preeti and Stefan were saying, there's a lot of non-physics types of stuff. There's chip design, for example, is a critical skill. Programming is skill. Most of quantum computers are programmed with Python with some stuff added onto it to do the things. But people look at a full stack of a quantum computer that starts with a chip at the very bottom and goes up to all the control electronics, the refrigerators, which requires mechanical engineers, by the way. How do you package it? IBM has spent a lot of money, for example, in figuring out ways of packaging their quantum computers, all the way up to creating libraries and user communities. So it's a large effort, and companies need to put together what's called a full stack, from the very application libraries at the top to the chip at the bottom, and either they do it themselves, like IBM, for example, can do it themselves, but many other companies, like the startups, just concentrate on a piece, and they'll partner with other companies that might help them with the control electronics. So there are a lot of different things that go into a quantum computer, and to be successful, you need to assemble them all together so they all work together.
Okay, great. So for my own selfish needs, I'm going to ask a question related to your favorite startups, right? So maybe you can give a view of, Doug, I know you've been tracking these startups. Your website has a large database of startups, so that's one of the good things about your website. Pretty, your Duality Accelerator, are always in front of startups and people applying. And Stefan, you are a startup, so you're probably you're coming out of Google and Alphabet. You guys are already exciting. I wish I could have gotten in, but I couldn't get in. But anyhow, so I'd like to hear, what are your favorite startups?
One's in Duality Cohort 1 right now.
So maybe you can
I
mention a few.
Sorry.
So maybe you can mention a few, Pretty.
Sure. So I think I'd mentioned that we have this accelerator program based out of Chicago. We have it's a 12-month program that's dedicated to quantum and enabling technology startups, hardware and software. So we have 6 startups in our first cohort. 2 are hardware startups. One's building a quantum random number generator based on kind of an optical version of it. Axion Technologies. One is a materials company building synthetic diamond materials, which have a number of applications, both in quantum and high frequency electronics, things like that. So Great Lakes Crystal Technologies. We have 2 companies that are sort of enabling software companies, building simulation software for designing quantum components, quantum sensors, or quantum photonic components. So QuantCAD and QuantOpticon. And then we have 2 more kind of traditional quantum software companies, QBraid and SuperTech. So QBraid has built a platform, like a software development environment where you can access other quantum computing platforms. They've been working with a lot of hackathons, providing a platform that others can use to program on. And then SuperTech, which is kind of doing some cross-stack optimizations. How do you use resources more effectively, and exploring applications in finance, energy, and other spaces like that. SuperTech is also a U Chicago spinoff, so I've been working with them for longer than just the 1 year. And I think they're a fantastic set of companies for our angel investors out there.
Awesome. Doug?
It's sort of like saying which of your children you love the most. There are a lot of good startup companies out there. I will concentrate though on just one aspect of quantum, which I think is important. We were just talking a minute ago about how it's critical to get a workforce and to hire people, and there probably won't be enough expert people to be able to take advantage of quantum technology. But there's 3 companies I'll mention that are concentrating in the software area to make quantum computers easier to use by allowing you to program at a higher level. So you don't have to get down into the individual gates to be able to program them, but you can do it much simpler. So if you're a content expert, for example, you could specify something, what the problem is, and the software will do the rest. So the first company I would mention is a company called Multiverse Computing, which specializes in financial software. And they've come up with an interesting product where you can input the problem with an Excel spreadsheet. If you're doing portfolio analysis, for example, you would just create a spreadsheet that has the parameters, the various components of the portfolio, and maybe the alphas and betas and stuff like that. And then you submit that to their software, and their software will do the rest to tell you what the optimal mix of those are. So, would be a good thing to help expand the usage of quantum. The second is a company in Singapore called Horizon Quantum Computing. They are developing software that will take standard C++ code, classical C++ code, and convert it to quantum. Look for things like loops that they could parallelize and stuff like that. So, it's a very difficult problem. I'm not sure they'll be successful, but if they are, that could open the door, particularly when the big computers are available, could really open the door for people moving a lot of the applications to quantum just by taking your old C++ code, or I think they also work with MATLAB, and converting it, having their program converted to quantum and run that. And then the third is an Israeli company. It's called Classiq, CLASSIQ, that has developed a high-level programming interface for quantum. So, again, you don't have to get down at the gate level and figure out, the minute details it takes to optimize your program to run, but they'll do it for you. So those are just three. I mean, I have, there are plenty of others that work in algorithms and hardware, but I'd be here all day if I I mentioned more.
Maybe I'll mention just a couple that spun out of Harvard recently. One is in sensing, and that's QDTI. So QDTI is interesting. They're using, a NV Center and Diamond platform, which is one of these platforms like superconducting qubits is a platform, ion traps is a platform, but the diamond-based platforms are potentially interesting, for people have looked at them closely for sensing and communications, especially. And QDTI is an interesting company that's looking at using diamonds for a medical diagnostic device, which could be a more near-term thing than computing. And I think it's an interesting company. And another one coming out of the same lab at Harvard is Quira, and they're doing computing, but they're using another platform, sort of the neutral atom platform, quantum computing using neutral atoms. And neutral atoms it's less mature than the sort of the superconducting qubits or ion traps, which get most of the attention, but could have advantages down the road when it comes to scaling. If the important thing is to get to millions of qubits, then maybe the important thing is to think about the platforms which can scale the easiest. And it remains, I mean, nobody has solved the scaling problem yet, but there are reasons to believe that maybe something like neutral atoms might be easier to scale. Who knows? But anyway, that's an interesting company that's working on the neutral atom platform.
Okay, great. Well, now at least I have at least 9 companies to look at, right? So, and we have additional investors here in this space. I think so I know we're a little bit over time, so maybe what we could do is just wrap this up and just get your. I'd like to hear for each of the panelists your final word related to the quantum industry, right? In terms of whether you feel bullish about it or bearish about it. I'd like to get your final word on where the quantum industry is heading.
Oh, I'll start. I mean, I'm being in the quantum industry, I hope I'm bullish about it, and I am, but I would be very careful. I mean, there's, like in most industries that are cutting edge and very exciting, there is a lot of hype, and at some point, a lot of people are going to end up getting disappointed, like it always happens. The bubble will burst at some point. Exactly when, I don't know, but it will happen. That's not going to be the end for quantum. Quantum will still continue. It's going to pay off in the longer term, but in the near term, please be careful of aspects that make it overhyped.
Yeah, I think I'll build on that. I definitely believe, like, in the long term, this is what's happening right now is going to be wonderful. In the short term, there will be losers, there will be winners. But you have to wait for the long term. And the one thing I always think about is this industry right now, because of the hype, it's attracted a lot of attention. It's attracting a lot of the talent. A lot of very smart people are actually working on some very hard problems. maybe those are not the right problems to be thinking about. Maybe the startups they're on will not last beyond the next 4 or 5 years. But I think we're creating a talent pool doing this. This is all good productivity. Like this is all going to be good for us in the long run. We're training people who will go on to be working on more interesting things, and will create an industry that we can't imagine right now. So.
Yeah, and one thing I would say is this is a new technology. It's still very, very early. And from an industry structure standpoint, it's going to follow the path that we've seen before in other high-tech industries, like automobiles in the 1920s, or something like 20 or 30 manufacturers, and they either merged, some went out of business, some it did well. We saw that in the early semiconductor industry when out of the 1960s and 1970s, when a lot of companies left Fairchild, some of them went out of business, some of them merged, some of them like Intel and AMD have stayed around. So you're going to see a very, very dynamic industry. You're going to, we've already seen a handful of mergers over the past year. We'll probably see more, but you also see companies go out of business. But you'll see some companies that will come up with surprising advances that no one predicted. So it's going to be very exciting, but it's going to be very, very dynamic.
Okay. Well, that's definitely a wrap. So Doug, Priti, Stefan, thank you so much for your knowledge and insights. I have 9 companies to look at as a follow-up for me. I think I'd like to pretty much turn it over to Chris if there are any TCA-related announcement that you'd like to do, or otherwise we could definitely just be done.
Thank you, Nardo. Thank you very much for moderating tonight's event. Again, right before I get into the TCA administrative things, I want to say thank you. And also for those who are interested in learning more about quantum, Nardo is a great resource. I'm sure he will be happy to connect with you offline. Feel free to reach out to him directly. The next event will be on May 24th. Much less sexy topic, but important one related to tax. And we'll be talking about employment retention credit, ESG trends. We'll have one of our sponsor partner from KPMG. We'll talk about some of these important topics for investors. So on that note, I want to thank you for the great panel tonight, and thank you for all the individual panelists for taking the time, taking your time out of your busy schedule to speak with us. Thank you, everyone. We'll see you next time.
Okay, thank you.
Thank you. Thank you.
Bye-bye.
Thanks for having us.